Thanks for the invitation. I think this is my first non-Zoom talk for a while, and need to get used to it. Okay. So I think has been realized for quite a while that inflation is actually a very interesting stage for all kinds of new dynamics, not just the inflation itself. And I think if recently there have been lots of work on this aspect, which is focusing on the fact that the inflation during inflation period and the Hubble can be as large as 10 to the 13 eV, and it can produce heavy particles that leaves a distinctive signal. This is an area cosmological collider physics. And there's another aspect I think is very interesting, is that the inflaton itself, we will detail later, can actually travel quite a large distance in the field space. And in principle, if there's some other spectator sector that couples to the inflaton, this can trigger something quite interesting in those sectors. So it is this second aspect I'm going to focus on, namely the drama in some spectator sector induced by the fact that by the rolling inflaton. Okay. So here is a simple estimate about how far the inflaton will go in the inflation, and of course this this is the number of E-fold, and depends on some slow parameter. But if we are not thinking about scenarios that this is absolutely tiny, then I think the inflaton field itself can actually travel quite a large distance. And even if we, for some reason we want to restrict it to, for example, delta phi less than Planck, this is still a significant movement. And yeah, even if we only consider a tiny bit of the inflation, like say order 1 E-fold, okay. The question is, are there any physics, observable effect coming from this change? I would argue generically there will be. And for example, let's consider this, I think, a fairly generic scenario. And here is my inflaton sector. And we don't have to consider anything fancy, just perhaps just some single field slow roll model, and with some approximate shift symmetry, all the good things you want for the inflaton model. On the other hand, there could be some spectator sector, which I just collectively denote as some sigma, but this can be even more complicated than 1 degree of freedom, obviously. And these two sectors in general have some couplings. Okay, so the couplings can be weak, and for example, the coupling can be induced by integrating out some new physics at some high scale m. And then the coupling can be generated in general of this form. Okay, there's some function of phi over m times, for example, a mass term looks like a mass term for the spectator sector. This looks like a quadricoupling for the spectator sector, right? So, and when the inflaton is rolling, especially going over some large distance comparable to the scale m, this will actually give you a significant modulation of the parameters in that spectator sector. Okay, so this does not destroy the fact that the spectator sector and the inflaton are still weakly coupled, because if you turn this field and consider this field not as a background but actually as an inflaton field, this is still, the coupling is supported by this this high scale. Okay, so but if I give you, imagine that this will be like, imagine I give you knobs to change, for example, the mass and the couplings of some spectator sector by order 1. Okay, you can imagine something dramatic will happen. Okay, we can imagine many different things, but let me just consider this very simple toy model. So this is, let's say, the spectator sector is just some simple single scalar model, and right, and plus a inflaton. And I also, just as a toy model, I consider the inflaton coupling just through this term. Okay, so this is some bare mass for the spectator sector, and this is the inflaton coupling. As I said, generically, I expect this coupling to be suppressed by some high. So indeed, this C number is can actually, depends on 1 over capital M squared. It can be pretty small. Now, when the inflaton is rolling, this effective mass can have an order 1 change. Okay, in this case, if I pick the quadratic coupling to be negative, this can actually trigger a phase transition, and for appropriate parameters, this can be a first order phase transition. Okay, so that's just a toy model. We don't have to, take this too seriously. It's just there to demonstrate that such model can be quite generic. Okay, so let's consider possible first order phase transitions during the inflation. So you want there are some requirement on this kind of model parameters. First of all, you want the phase transition to at least happen. Okay, have a order 1 probability to happen within your Hubble volume. So this is achieved by comparing the phase transition rate, which is depends on some characteristic scale in the spectator sector and the bounce action. And for the phase transition to be efficient, namely for it to happen, you want this quantity to be order 1, and this means that you want the bounce action to be this order. And you can relate this to some slow roll parameter and the scales in the spectator sector and the Hubble parameter, right? So for the phase transition to be first order, typically, and you want the bounce action to be big, right? So this means that you want this ratio to be big in general. So you want the scale, the spectator sector, to be quite a bit larger than H. On the other hand, just to simplify our consideration, we don't have to stick to this condition, but just to simplify our consideration, we can think about this as just a spectator sector. It does not disrupt the inflation that much. You want the energy density in this sector to be much less than the energy stored in the inflaton sector. Okay, so this will be in requirement. You see that there is quite a bit of a parameter space that this can happen. And it turns out that this is a little bit too simplistic. What we want more is not just one nuclear or one bubble to be nuclear in one Hubble volume. We wanted this to happen often enough so that the phase transition, in the end, when the phase transition finishes, the bubble actually occupies order 1 fraction of the Hubble volume. So this is typically done by the following. We can expand the time dependent because the time dependent. In general, there's some time dependence on the bounce action, and we can expand this by around the time that the phase transition finishes, and this introduce this beta parameter. This is basically the inverse time if you want a bubble actually expand, and therefore the inverse of this is also sets the typical size of a bubble when the phase transition finishes. Okay, so this is a very important parameter. So a more careful analysis than the one that I just presented on the previous slide tells you that if you want this the bubble in the end, the true vacuum in the end occupies a order 1 fraction of the Hubble volume. Instead of wanting this typical scale of the spectator sector to be much greater than H to the 4th, what you really want is to be much greater than beta to the 4th, than this scale to the 4th. Okay, and this requirement we still impose. Second requirement. So what is the typical beta that coming out of this kind of models? And so here is a simple estimate. I just write the derivative of the bounce action with respect to time over h in terms of this. Basically, you do a change of variable, and you trade the derivative of time with the derivative of mass. And this is the derivative of mass with respect to time, which in turn depends on phi dot, which is epsilon 1/2. Okay, so that's and this is the rest of the factors. So this can you typically obtain by some numerical simulation. So for example, if you plug in Cosmos transitions, they will tell you this number is roughly order 1. Okay, and this is usually too small. It is somewhat less than 1, but it's not too small. And usually when you're getting close to the phase transition point, there is a bit of a tuning between these two contributions to the mass of the spectator sector. So this number is usually in the bracket is usually sort of unnaturally small, a little bit than its natural value. So hence the beta usually ends up to be quite big, on the order of 10. So beta over h is on the order of 10 or 100. Okay, typically that's the typical number that we get numerically. Depends on the other parameters in this simple model. Okay, yeah. So this is again, remember this is a requirement, and now the beta is should have in mind is roughly tens, a few tens times h. And yes, there is still plenty of parameters within this range to have my scale, the scale of the spectator sector to have this scenario. And this is just showing you that the numerical simulation tells you that yes, if you satisfy this condition, indeed the order 1 fraction of the Hubble volume is occupied by the true vacuum within a fraction of a Hubble time. Okay, so. Yeah, and the transition, through from no phase transition to fully occupied is pretty fast. Okay. So what is the general picture? The general picture is that I have the radius. So I have a, after phase transition finishes, I make a bunch of bubbles. The size of the bubble is much smaller, order 10 or 100, smaller than the size of my Hubble volume. Okay, these are small bubbles, and they will collide, right? So, and the collision time, the duration of the collision, you can use a simple estimate is roughly set just by the size of the bubble. Okay, so these all propagate with speed of light, and so this is the so these collisions. From first order phase transition will generate gravitational waves. Moreover, the gravitational wave source happens for a small duration, okay, in comparison with the Hubble time. So more or less they are instant. You should be thinking about this as almost like an instantaneous source for gravitational waves, okay, for this kind of phase transition. Okay, so what do the gravitational wave signal look like? So qualitatively, we should think about them in 3 regimes. And there is the intermediate regime where the wavelength of the gravitational wave is somewhere between the typical size of the bubble and the Hubble radius. Okay, that's what we call the intermediate regime. Okay. And there is a IR regime where the wavelength of the gravitational wave is bigger than the Hubble radius. And then there is a UV regime where the wavelength of the gravitational wave is shorter than the typical bubble size. Okay, so there are these 3 regimes. And well, you can get because this is almost an instantaneous source, at least in this limiting case, you can get an exact analytic solution for quasi-de Sitter space-time. And we'll talk more about the qualitative behavior of these solutions much more later, but you see what there are a few things. There is some oscillatory piece, right? So there's for example, And yeah. And this is during inflation. This is what gravitational signal look like during the inflation. And this is then after inflation, the reheating, and the gravitational wave will still propagate and re-enter the horizon, eventually being observed by one of the gravitational wave detectors, assuming, so what gravitational wave look like also depends on what the evolution of universe and after inflation. So assuming, for example, radiation domination, so the gravitational wave will have an additional factor like looks like this. Okay. So let's just talk about the qualitatively what the behavior in these three regimes are. So in the intermediate regime, so you can still in the intermediate regime, you can still think about this source as an instantaneous source because the duration is much smaller than the wavelength of the gravitational wave. And this is so what you think about is that you're exciting all the mode at the same time, then they start to oscillate, and the amplitude will freeze when they exit the horizon. So exactly what the amplitude is depends on what k is. Okay, in the end, so therefore you should expect the signal in this regime should look like some oscillation in frequency. There's oscillation in frequency, okay, or in k. Okay. Yeah, this is just another picture of the same thing. Let me not spend time on that. Now in the UV regime, when the wavelength of the gravitational wave is much smaller than the typical time scale of the bubble, or smaller than the size of the bubble, then yes, individual modes are still oscillating, but the finite duration becomes important. Okay, here you expect the oscillation to be smeared out, just because there are multiple sources happen at around different time and so on. Okay, so that's what you expect. And the infrared, when the mode is already outside the horizon, okay, when the phase transition happens, so there's the mode that's longer than the size of horizon, it will not oscillate. It will just stay as a constant. It will start to oscillate when they re-enter the horizon. Okay, so that's what you expect in this regime. Yeah, anyway, so this is just another picture. Just repeat, there are these three characteristic behaviors. Here you have oscillatory, this is constant, there's no oscillation here. Okay, so then the shape, this is of the gravitational signal as a function of frequency is also interesting. So let's also understand that. Again, I will divide this into IR, intermediate, and the UV regime. So in the IR regime, and it's a constant, right? Because it does not evolve because it's already outside the horizon. And it only evolves after it re-enters the horizon. And this is just remind you the gravitational wave, differential gravitation power in the gravitational wave, d rho d log k is given just proportional to this simple formula. Okay, so use this and that, you can see that the slope you see in the IR, you expect a k cube dependence in IR. And that is actually pretty universal, okay, because it really doesn't depend on a lot of other things. And in the intermediate regime, yes, we have oscillation, and the gravitational wave. This is the oscillatory piece that we talked about, and moreover, there is an additional k square just coming from the evolution Green's function during the inflation, and this is the factor for evolution after inflation. And using this, you see that there is the envelope here has a k to the -1 dependence. Okay. For the UV part, this part we couldn't quite do it analytically because the detail of the bubble collision is important. So we have to rely on some numerical simulation. Fortunately, people have already done this. Okay, not in this particular problem, but people have done the collision in flat space. But in the UV case, really the curvature of the space is not that important. So the flat space result should apply. So if you use that, you see that this depends on k to the minus 5. Okay, so there is also a piece depends on the evolution. Okay, yeah. Okay. All right. So okay. But let me. I think all these things are very important. Crucially enters here is that I'm assuming the inflationary space-time is quasi de Sitter, and after inflation, immediately after inflation, it's a radiation explanation. Yeah.
I'm a little confused in the sense that I would have expected that if this is happening during inflation, some of these modes would be exponentially suppressed.
Right.
But everything here is power law suppressed. So kind of what's going on about that?
If you go through it carefully, it's not exponentially suppressed. Okay, so it depends on. So for example, for the mode, exactly of the size. So let's see. So for example, at this point, right? This is the highest point of that the mode the wavelength is exactly the same size as the horizon. In that mode, immediately exit horizon. Okay, it does not get the the amplitude gets fixed, that gets freezed. The energy does scale like 1/8 squared. Okay, so but even if you take that into account, yeah, it doesn't matter when. It doesn't matter when it matters when it exits horizon between the creation and exit horizon. Yeah, so the energy, so it's 1/a to the fourth, but a to the fourth, what is it's the a to the fourth is the a when it's produced versus the a to the horizon. Okay, there is a bit of a suppression for that, but it's not the way to the end of inflation. Okay, so it's just the period that has been taken into account. Yeah. The Green's function I had there is actually general. It has all this effect in it already. Yeah.
With that discussion in mind, can I think of this gravitational wave background as sort of a perturbation on the initial conditions set by inflation, essentially? Because those are,
Yeah, so this is different from the one that generates by the gravitational oscillation during the basic. Yeah,
it's essentially adding that to the initial conditions in some sense, which then spreads out as soon as the mode.
Yeah. So this is like an instantaneous burst of gravitational wave from bubble collisions. So it's very different from.
So I'm not used to thinking about. So in my mind, I'm used to thinking about gravitational wave spectra in terms of frequencies, temperature, and whatever. So this is different. So in this way of looking at it, I'm struggling to translate this to a sort of physical spectrum, but we haven't even gotten there yet, right? We haven't yet gotten to the physical spectrum that I see today.
Well, this is sort of the physical spectrum, and the actual omega is this over whatever the
actual omega is okay.
Yeah.
How would this plot? So this model that you're describing in my mind has two physical parameters, which is the stage of inflation when this happens, so like the number of e-foldings or the Hubble radius or whatever during inflation when it happens.
This is the tau star that we're talking about.
That is the tau star. Okay.
Sorry. Now my page is not turning. But,
okay, good. So tau star is when the inflation happens, and then there's the average number of bubbles.
No, when the phase transition happens.
Sorry, when the phase transition happens.
Yeah. Then there is the average number of bubbles.
Average number of bubbles. Good. Yeah. So if I twiddle tau star, then this whole thing just shifts up or down. No.
You twiddle.
So if I change tau star, this whole thing I think just shifts up or down. Does it?
Well, it's the
side to side.
It's the frequency that's changing.
Yes.
It's the frequency changes. The frequency of the oscillation in K changes.
Right.
So this is K. Then this K will be redshifted. That becomes the observed frequency of the gravitational waves. Yeah.
I see. So tau star influences how this eventually becomes observable frequency.
Yeah.
What happens to this plot if I change the number of bubbles per volume during?
Yeah, so the overall amplitude will change a little
Oh,
bit.
so that's just the overall amplitude.
Overall amplitude will change a little bit, and you will see maybe
Okay.
there's some examples.
So
Yeah.
there's some more questions online.
Hey, so I wanted to ask about so the following thing. So are the most of the gravitational waves produced during inflation, or are they produced from secondary? Are they produced as secondary gravitational waves once the modes re-enter the horizon, and then and then they are produced from second order as a second order perturbation?
No, it's a. I'm imagining there is a sector that undergoes a phase transition during the inflation, not the inflatons, but
No, I understand.
Yeah, so it's just coming from the bubble collision.
No, but what I mean is that the bubble collision also produce a scalar perturbation in the primordial spectrum, and once those modes re-enter the horizon, they themselves can produce gravitational waves, right? So they should produce also a huge scalar perturbation, not only a tensor perturbation, which corresponds to these bubbles. And as far as I understand, both of these scale sort of the same way, because they would scale like the energy density in the phase transition squared.
Yeah, so the one that's included here is from bubble collisions. So
I see.
Yeah.
But shouldn't you also then include the effect of bubble collisions and bubbles themselves on the scalar spectrum, and then include the effect of the scalar spectrum on the tensor spectrum?
Sorry, could you ask?
So what I mean is that the bubbles, right? They produce a inhomogeneity, right? So you are calculating the tensor inhomogeneity, which is the gravitational waves, but they also produce a scalar inhomogeneity, which is just the fact that these bubbles are there. They'll produce some gravitational potential, some phi, and so the question is that phi once those modes freeze and re-enter the horizon, they themselves can produce now gravitational waves after inflation. Like for instance for primordial black hole production, and the gravitational.
So that part I don't think we included. Yeah.
I see. Yeah. Okay, thank you.
Hi, Liantao, can you hear me?
Yes.
Okay, so sorry, probably I missed something at the beginning of the talk. So as far as I remember, Guth-Weinberg's result is if you have bubble nucleation, they don't collide, and
yeah,
the
so
space inflation.
Yeah, so that's the case when they want the tunneling rate to be small. Okay, so their result is a probability that depends on exponentially the tunneling rate. Okay, so they want the tunneling rate to be small because they want the phase transition to be actually in the inflaton sector, and then they want the inflaton to stay in the force vacuum long enough to solve whatever problem that the inflation designed to solve. So that's the old inflation problem. Okay, so it doesn't exist here because I'm considering phase transition in the spectator sector. It's not even driving the expansion. Okay, the energy density in this spectator sector can be, for example, just 10% of the inflation sector.
Okay, thanks. I see what you mean.
Okay. Yeah, so the really characteristic part that tells you that there is an instantaneous source is this oscillation part.
I get that, but I would like to know in frequency, the range at which you can see it. So in other words, in mind, I can see this.
Yeah, I'll show you a plot later, much later. Okay, I don't know. I'm already 1 minute over time, but if I get there, and I'll show you later. Yeah, yeah.
The way to think about this is as this essentially adds. Sorry. So just to be clear on this. In either case, the way to think about this as gravitational wave production is as giving you new contributions to both the tensor and scalar perturbations initially. And then that is, I can interpret the new gravitational waves that way, the same way that I get gravitational waves from inflation.
Yeah. So, yeah. But you see, it's a very different, and the kind of shape is
okay. So it's a very different set of tensor perturbation initially.
Yeah. So
we should try to speed up.
Okay.
No, it's fine.
Yeah. So okay. So I'll let me just maybe I will skip something, but let me just emphasize that all these actually depends quite sensitively on my assumption that I'm in a quasi de Sitter. I instantaneously repeat, and it's after that is radiation domination. Okay, all these things. Okay, and this is not turning, so can I do it manually? No. No. Okay. Yeah, let me just skip this. I'm just, I wanted to emphasize that there is a lot of dependence on the later evolution of this whole thing. So we sort of package this into these two factors, and this factor determines the, parameterize the dependence on the gravitational wave signal from its production through the inflationary period. This parameterizes the dependence on the evolution after heating. Okay. Yeah, so you can try to, this actually give you a kind of interesting possibility. You can use the shape of this kind of gravitational wave signal to probe the subsequent evolution of the universe. For example, this phase transition doesn't have to happen in any of the CMB or era that where the CMB mode or large scale structure mode get generated. It can happen much later after that during the inflation, like say maybe 10 E-fold till the end of the reheating. So normally we don't have real observables to get you a handle on those things, but the shape of this spectrum give you some kind of a handle before. Also, this can give you some handle before the BM, for example, of the evolution. Normally, we also don't have that much observation handle on this kind of a scenario. So if there is such a phase transition and a gravitational wave signal, it will be, I think it will be a quite exciting opportunity to use this to probe the evolution of the universe after the phase transition. So just for comparison purpose, you can think about maybe there's a quasi de Sitter. This is what I assume, but maybe you can compare it with some power law inflation, just parameterized by some power P. And the P goes to infinity limit is roughly the quasi de Sitter case. And also you can contemplate many different exotic scenarios after inflation. So radiation domination is the standard one, but maybe also matter domination. There's matter domination period, which is quite generic, but even more exotic scenarios. Yeah, let me just, so you see that the UV part of the spectrum, so this K to the -5 is the one that I just discussed, assuming radiation domination for the de Sitter case. And for matter domination, you already expect a different power dependence on K. And this is a more general formula. And for P, T to the P inflation, these two are also different. And for the intermediate part, again, this K to the -1 is the one that we talk about as a benchmark. But if it's matter dominated, you'll expect a different power. And for the infrared part of the spectrum, it actually does not depends on the inflationary scenario because the mode is already outside the horizon. It doesn't really depend on how space is expanding. The K dependence doesn't depend on that, but it does depend on how the space is evolving after the reheating. Okay, to have a different power. Yeah, so for example, this is a case if I instead have going from a de Sitter inflation, instead going directly to the radiation domination, which is the purple curve, which you couldn't quite see here, but I have some intermediate matter domination period. Okay, and then transition into a radiation dominant period. This is quite generic. For example, if you imagine just inflaton is slightly long-lived, and this will be actually quite generic. And you know, you see that the spectrum is actually quite different. Depends on when this transition happens. Okay, I think I'm. And you can also make a similar comparison between various different inflation cases. You see that the infrared part, as I said, it does not really depend on the inflationary scenario, but the intermediate and the UV part does depend on them, okay, quite sensitively. So if you observe this kind of gravitational wave spectrum, it's actually, this oscillation part will tell you that this scenario is correct. There is a sort of a first order phase transition during the inflation. Then you can try to use the rest of the shape of the spectrum to learn something about the evolution, the time evolution. Okay, yeah, so this is superimposed on some sensitivities of a future experiment. And yeah, so it's pretty futuristic, but I think it's possible. And so for example, again, you can consider, this solid brown curve is our first benchmark. You just have to consider going through radiation domination. And then for this set of solid curves, you have a matter domination before radiation domination. Because there's extra redshift during this matter domination period, the frequency, the peak frequency itself actually shifts to lower value, and also the shape of the spectrum looks quite different. Okay, so that's the end of my talk. And so I think, again, I wanted to emphasize cosmological observations actually give you really interesting windows to new dynamics in the inflation era. So in this talk, I emphasized this aspect. So potentially large inflaton excursions can actually trigger new dynamics in a spectator sector. For example, one of those new dynamics could be a first order phase transition that leads into interesting gravitational wave signals that I spend some time describe. It has a very distinct shape, and it's really very interesting probe of the time evolution after the phase transition. Okay. Thank you.
I mean, we have Ben that might to talk, because like his talk was scheduled for like very soon. So Ben, are you there? Because I know that you probably have time constraints. So if you wanna,
I'm here.
Ah, okay. So then we proceed with questions. What? Ah, do you want to talk just after this talk?
That's not the right.
What, can you hear? Okay, do you want to talk like just now? Later. We can just switch together with you and Philip.
One quick question. So you mentioned that this phase transition is happening in the spectator sector. So for your plots, what were the assumptions about the energy density in the spectator sector?
Yeah, I think we take 10%. Obviously, the overall density was scale up and down. So, I mean, in principle, there's no hard limit. I think this is a conservative. I don't want to change the much. Again, this could, in principle, happen way after all the observed mode, the CMB and the large scale structure mode has exit horizon. So there's, in principle, there's no constraint what's happening here. So, yeah.
I see. So this is
Yeah.
kind of related to, I think, what Michael was asking earlier. I think if I am interpreting it correctly, he was thinking about sourcing curvature perturbation due to like scalar curvature perturbation when the phase transition happens. But I guess, yeah, if you're doing it in the spectator sector, there would be some sort of suppression because
because
when
sure,
yeah. Right.
So anyway, this is a conservative scenario, but I guess if it's larger, then perhaps what he's asking is more,
Yeah, sorry, maybe I missed it. So the frequency peak, what's that set by? Is it like the temperature or the scale of inflation, or?
Yeah, it's where the two slopes meet.
Okay.
Right. So our spectrum grows like k cube. The intermediate dies like 1/k. So just these two, when these two meet, it happens that the transition between them, the frequency is when the wavelength is exactly the same as the Hubble.
Right.
Okay, so that's when where the transition between these two behavior happens.
Yeah. Okay. But so like these the ones that peak in the space-based interferometer range, they're all the low scale inflation models, or?
The scale of inflation here it does not. It enters the scale when the inflation enters. Sorry, the scale. The scale during the phase transition enters setting the frequency, setting the transition frequency. Yeah, you're right. So the H at the sets where the peak is. Yeah, that's
exactly.
Right.
But that's a relatively low scale, I guess, or it's
the picture you see for the last picture is H is 10 to the 8 GeV.
Okay.
Okay, I don't know whether you call it a low scale or high scale.
Okay, sure,
Huh? Can we go back a little bit? I mean yeah. No, go back. I think yeah, this is going forward. Yeah, so this is the whole thing is for 10 to the 8th. But this is the de Sitter to radiation domination. This has this lower frequency because you have an extra period of matter domination. So I have an extra redshift. Okay.
Can I mean, like there seems to be some degeneracy, or
if you have an infinite precise measurement, you can, right? So
Okay.
because whether you have matter domination also enters the slopes here.
Right.
So you can already see it. So in principle, of course you see the gravitational wave first. Okay, then gradually the hope is that you see some oscillation. You derive there's some this kind of phase transition happens. Then after that, it's very predictive. You can predict the whole spectrum. You can try to okay.
Does the reheating temperature enter here at all?
In the sense that this assumes instant reheating. Yes, it does enter. It does enter here. Yeah.
But the absolute reheating temperature can be shifted arbitrarily.
Instant reheating means that all the energy convert into radiation. That's the reheating temperature.
Right. Sorry, I guess right. But even within reheating temperature, I could have a different reheating temperature for different inflationary models.
It depends on the scale. Yeah. Then if it's instant reheating, it just depends on the scale of what energy you have, right? So then it's just completely converted into radiation. Yeah. So then if you have a little bit of a radiation domination, then it's a smaller. Yeah. That in that way it enters.
Okay. Thank you.
You could if the phase transition happens earlier, during the CMB period, of course you could. But in the CMB period, there are also other observables, right? It's a very interesting question to see which one is more sensitive, right? So what's sensitive to what? In CMB, we have lots of observables, right? If you have a spectator sector, that it does have some back reaction on the inflation sector. So you have to be, yeah, so it'd be consistent with that, then have this. Okay, it's possible. Maybe it's still possible, but it deserves a much more detailed study than this. Yeah.
Hi, Liantao. So this effect, how do you distinguish this effect from, for example, some sharp feature during inflation? Any arbitrary sharp feature?
I think if you have a depends on the duration. If you have a short source, short instantaneous source from of gravitational wave, then this will be the same, right? So all this does not depend on this phase transition model that I present, right? I just show you that model to show that this is not crazy, but as long as you have a short gravitational wave source, this is the same.
Okay, so the Tij, the energy momentum.
So for the sharp feature, it depends on how sharp it is, I would say.
Yeah, for example, just also instantaneous. Yeah.
Then it will be the same, and we have to estimate the strength of coming from that. Yeah.
Okay, so let's thank Liantao again.